Hello everybody, I hope everyone's doing well. For today's video, we're going to spend our time talking about quadratic functions. Right? So we've talked about quadratic equations before, and now we're simply going to take everything we talked about there and shift it over into functions. And then in addition to this, we're also going to tack on this idea of standard form. Alright, some of you have also probably heard this as being called Vertex Form. Okay, and that's pretty much it for today. So, why don't we go ahead and get right on into it. Alright, so before we actually get into quadratic functions, I want to go ahead and take some time now to finally define a word and a phrase we've been using quite a lot in this class, and I kept on pushing off, and that is the idea behind polynomials. So what actually does it mean to be a polynomial? Let's finally go ahead and write that down. So, as always, I'm going to introduce a new topic or a new definition, and so we're going to do this using abstract or general notation. To accomplish that, we're first going to say let A sub n. So that's an A sub n. It's like if you don't know sub notation, you have, let me go ahead and inflate it a bit larger. So you have your A, and to write it sub, it's kind of like the opposite of a power, so that was the power of 2. To do a sub, it's kind of right below it. So for those of you unfamiliar with sub notation, that's what's going on there. So if A sub n minus 1, dot, 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 A sub 2, A sub 1, and A sub 0. So we have this whole list of A's, okay? And we're going to let them be real numbers. So all these A's are real numbers. Be real numbers. But we're going to have a condition. And the one condition we're going to have is that these A's can be any real numbers they want to be, except and A sub n can't be 0. So, they can be any number they want to be as long as A sub n isn't 0. There you go. So with that, then we get to say, then f of x, so our function, and we're going to say our function equals A sub n times x to the n plus A sub n minus 1 times x to the n minus 1 plus dot 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 plus A sub 2 x squared plus A sub 1 x plus A naught. Alright, then we're going to define our function f of x like this. It's basically taking the A sub n and whatever the sub notation, the sub value is on n, or is on the A, so here was n, we're going to multiply that by an x with a similar power. So what am I getting at? Here we had A sub n, the sub was n, so we multiplied an x with a power of n. Over here, we have A sub 2, so the sub was 2, so we multiplied by an x with a power of 2. And we're actually doing it over here as well. We have an A sub 1, the power is 1, so we're multiplying by an x to the 1. But x to the 1 is just x, right? Same over here, we have an A sub 0, so I would need to multiply by an x to the power of 0. But x to the power of 0 just equals 1, because anything to the power of 0 equals 1. So that's the trend that happens. This is how we get to define our function. And this is it. This is what it means to be a polynomial, right? So we get to call, so if f is defined this way, then we get to say that f is called, oh, can't read that, a polynomial function, and here's the important part. We get to call f a polynomial function of degree n. To call it a polynomial function of degree n. And this idea of degree, we've mentioned it before in class, right? When I have a linear function, ax plus b, the degree of that function is 1. Why is that? The highest power in ax plus b, the highest power for our variable x, is 1. For quadratics, ax squared plus bx plus c. The degree is 2 because the highest power on x is 2. So we get to call our abstract polynomial degree n because the highest power is its value n. There you go. So this is what polynomials are. All polynomials are, in a nutshell, is adding or subtracting a bunch of terms together where those terms are a number multiplied by a variable with differing powers on the variables. That's all polynomials are. Nothing too horribly complicated. but incredibly, incredibly useful in a real-world applications. A lot of things can be modeled quite nicely by polynomials, and a lot of things can be modeled quite nicely using things called exponentials and logarithms, which we'll get to later in this class actually. But for now, we're talking about polynomials. So here we are. Now, one last thing to mention about this is that we have the degree. The degree n is determined by the highest exponent, and in addition to that highest exponent, we also have this a sub n value. That's the number or the coefficients being multiplied to our variable x to the power of n. And this a sub n gets its own term. I think I've probably mentioned it in class before, and if I haven't, well, I'll mention it now. So here's a nice note. We call a sub n the leading coefficients. So this is known, a sub n is known as the leading coefficients. Okay, so those are kind of the two always big important features in a polynomial, is its degree and leading coefficient. They actually give you a lot of information, and we'll see for quadratics what the type of information they give us is. So there you go, there's polynomials. So go ahead and take a moment now, pause the video, and get all this copied down if you haven't done so already. Beautiful. Now then, with that out of the way, let's go ahead and move on to our first example for the day. And for our first example, let's go ahead and we're going to identify the degree and leading coefficients for the polynomials. Okay? And the polynomials we'll be concerned with are, we'll do 3x plus 5. Make sure you can read that. We'll do 3x plus 5 and 6x to the 20 plus 18x to the 9. And then we'll also do 4x to the 4 plus 5x to the 7 plus 8x cubed plus 9. And then let's do, let's make all these functions actually. So let's say this is f of x equals, g of x equals, h of x equals, and v of x equals 5. There you go. So here are our 4 polynomials, okay? And we want to identify their leading coefficients and their degrees. So what I encourage you all to do now is pause the video. Pause the video and work this example out for yourself. Then we'll come back together and we'll talk about it together. It should be relatively straightforward. I hope none of you will have too much difficulty doing this on your own. And if you do though, that's no problem, because then we'll talk about it together right afterwards. So go ahead and pause and work on your own now. Okay, so let's go and discuss the answers. Well then, let's start here. As always, we go back to our definition. What is the degree of a polynomial? It's simply the highest power on the variable. So, we only have one variable to concern ourselves with here, so it's pretty straightforward. We only have one x. What is the power on that x? It is 1. Right? Because we remember that any variable that does not have an explicit power written means it's a power of 1. Any variable by itself is always an implicit degree of 1. So then, there you go. Now then, the leading coefficients. What is our leading coefficients? Well, it is always the value being multiplied to the x with the highest degree, or the highest power. So for us, the value of x, the value being multiplied to our x is 3, so our leading coefficient is 3. Okay? Similarly, for the problems over here, for this second polynomial, its degree is 20, because 20 is the highest power present, and then the leading coefficient is the number being multiplied by x to the 20, so it is 6. Alright? So, big kind of an important note right there is that the leading coefficient isn't the largest number. The largest number is 18. The leading coefficient is the value being multiplied to the variable with the highest power. So our highest power is 20. That makes the leading coefficient at 6. All right, and then for our next one, right? What is our degree, right? So it's not 4. So 4 may be the 4 times x to the fourth may be the term that shows up first, but the degree is the largest term or largest power, and so our largest power is 7, and so that makes our leading coefficient 5. All right, so always be careful. Sometimes when you're given a polynomial, it may not be written in ascending order with the largest power first and then decreasing powers afterwards. You may get some mad person who writes it in some scrambled order for some horrible reason. And then so lastly, we move on to the last one. And the last one's kind of a bit tricky, right? So what is the degree on Vx equals 5? Or V of x equals 5? Well, do we have an x? No. We don't see one written. But if we want to be super, super tricky, there is technically an x there, right? Because we note that 5 is the same as 5 times 1. And 1 can be written as x to the 0 power, because anything to the 0 power equals 1. So technically, if we want to be super tricky, we can sneak an x in there. And so that means our degree then becomes the power of this x, which is 0. So we have degree 0. And our leading coefficients, this is where it gets really weird. To me, coefficient is a value being multiplied to a variable. And technically, the 5 is being multiplied by an x to the 0. But when I look at the actual equation, there is no x. So I wouldn't blame you if you wrote 5. Me personally, I would say none. But, you know, just kind of one of those interesting debates of thought. Not too important to get hung up about, though. So there you go, right? So it shouldn't be too hard for us from moving forward when given a polynomial to understand what its degree is and to understand what the leading coefficient is. So with that then, with that out of the way, let's go ahead and finally move on into this topic of quadratic functions. Okay, so parabolas. Let's go ahead and briefly talk a bit about parabolas. Now, when we're talking about quadratic functions, so in the realm of quadratic functions, there's only 2 parabolas we're really concerned about. And that is this one. Or, and surprise, surprise, you're not going to expect it, the other one we're concerned about is this one. But none of you saw that coming. Yeah, so yeah, these are it. These are really the only 2 parabolas we're really concerned about when we're discussing it in terms of quadratic functions. Okay? And as I mentioned, there's some nice information stored inside parabolas. The key piece of information that's available here are these 2 points, A and B. Alright? So what's so special about these points? Why are they special? Well, they're special because, and they get their own name, these are the points in which our parabola changes behavior. What do I mean by that? Here on this side of A, we can see that our parabola is moving down. In other words, our parabola is decreasing. Then we hit A. And what's special about A is right after we hit A, after we move past it, our parabola starts increasing and it starts moving up. So these points A and B are the points, it's actually the only points, so just to talk about this one, that point A is the only point on this parabola where our behavior changes. That's really what's so special about that. So, as I mentioned, these points get their own special name, and we call A and B. A and B are called the vertex of the parabola. All right, so there's another new word for us today, vertex. So A and B, these are special points we call the vertex of their respective parabolas. Okay? And why do we care about them so much? Right? That's the point where the behavior changes. We have a decrease to an increase. Right? So not only are A and B vertices, but they're actually something, we can actually say more about them. Keyword behavior change. So A is a decrease before it, an increase after it. That is the exact behavior to classify as a relative minimum, right? So A is, in additionally to being the vertex, is the relative minimum, and B is a decrease. You hit B, then it starts. I mean, my bad. You increase before B, you decrease right after B, so B is a relative maximum. So nice little key point right there is that the vertices, or the vertex of a parabola, the vertex of a parabola is always a relative max or min. Right? That's going to be a key point for today. That's going to be following us. That point right there is something we're going to be using a lot throughout today. So, there you are. Just in case anyone didn't know, yep, here's parabolas. If you weren't familiar with this idea of vertex, there you are. And now we understand that when we're talking about the vertex, it's always a relative minimum or maximum. Now, one last note I want to leave you with to think on your own is this, right? So, think on your own. I said when we're concerned, at least when we're talking about quadratic functions, so for quadratic functions alone, these are the only two parabolas we're really going to be concerned about, all right? But there are other ways I can draw a parabola. Like I could draw a parabola this way, or this way, right? Just simply turn on the side instead of going up and down. But for quadratic functions, we don't care about these. For quadratic functions, we don't consider these parabolas. And so, my quick think on your own question for you is why? Why do we not care about or concern ourselves with those two types of parabolas in respect to quadratic functions? So go ahead and think on that on your own. But besides that, let's go ahead and move on now, and let's get into our next item of discussion. Okay, so now I want to propose a question, and my question is going to be this. Which function is easier to graph? Alright, and the two functions we're going to consider are f of x equals 2x squared minus 4x plus 7, and g of x equals 2 times x minus 1 squared plus 5. Okay? So here's our two functions, and I want to propose this question. Between the both of these, which one do you feel is easier to graph? So go ahead and take a moment, pause the video, just think about it. If you had to choose which one you would prefer to graph, would you rather graph f or g, and why? So go ahead and decide that now. Alright, so for me, I would say g is easier to graph. So my answer, g. Alright, why is that? Why? Well, the only feasible way I could think of for graphing f is to make a list of points. Alright? Or to make a table of points. But that's not the case for g. Why is that? Well, I can look at g, and what can I understand about it? I can look at g and I can say, wait a minute, this function g is just a translation of the parent function x squared. So as long as I know what the graph of x squared is, which I do, it's a parabola, I can just apply those translations, and just like that, I have the graph of g. So all it means to graph g of x is just going back to a couple lectures ago when we talked about translating functions and creating those graphs. That's all we need to do for g. While for g, I just need to translate x squared, right? What are the translations on g? We can list those off quite easily. So I have a plus 5 on the outside of the square. That's a vertical shift 5 units up. Right? I have a minus 1 on the inside. We understand that's the counterintuitive horizontal shift. So I'm not moving left, I'm moving right. Horizontal shift 1 unit right. And then I multiply by a value of 2 on the outside. 2 is bigger than 1, so this is a vertical stretch. And just like that, all I have to do is take my normal parabola, apply those 3 translations, and I have already constructed the graph for g. While on the other hand, for f of x, I would need to go through and create a whole list of enough points to get a good, accurate idea of how the graph looks, and then connect the points that way. So in my mind, it is much, much easier to graph g. Alright, so go ahead and pause the video now to take a note of these observations if you haven't done so already. Okay, now, here's the kicker. What's the big kicker about this question? And I'm sure some of you probably have realized it at this point. The kicker is this. I'm going to go ahead and erase this part. So this is actually a trick question. Why is that? Because in actuality, 2x squared minus 4x plus 7 is the same thing as 2 times x minus 1 squared plus 5. These equal each other. These are actually equivalent, alright? It's just 2 different manners, 2 different forms of writing the same type of equation, that being a quadratic equation. So, as we already mentioned, this way on the left-hand side is known as our general form. And then this on the right-hand side, this is our new form we're about to get into and discuss. This is what we know as standard form. Again, some of you may have heard this as vertex form, but there you go. So now let's go ahead, with that out of the way, let's introduce this idea of standard form. Alright, so standard form, or as it's also known as vertex form. Well, just like general form, all this is another way to express or write a quadratic function. So, what does it look like? Well, before we get into it, we've got to define these variables. A, H, and K. We're going to say that these are real numbers. So A, H, and K are real numbers, and as always, A can't be 0. Alright? Well, with that out of the way, then we can say that vertex form looks like this. F of x equals A times x minus h squared plus k. That is vertex form. Now, why do we go through the bother of creating this whole different way of expressing how to write a quadratic function? Why not just stick with general form? And the answer to that is, unlike general form, vertex form gives you a lot of information about the graph of your function immediately. You don't even need to graph your function. Just by looking at this form, I can understand some pretty key features about my graph. Well, what are those key features? Well, one of them's in the name, right? We call this vertex form, so unsurprisingly, right here, you can understand right off the bat what the vertex of your parabola is going to have to be. And what ends up happening is, I don't know why I wrote parabola. What ends up happening is that the vertex is guaranteed to be the point h, k. Alright? That's one of the big pieces of information you get to pull out of vertex form, is it just tells you right off the bat what your vertex actually is. And it's the point h, k. Now, there's one very important piece of information we need to note, and that is, in the vertex we use the value h. But inside the vertex form, we have minus h. All right? So take special note of the difference in signs. Here we're subtracting h. Here it's just the h value. So in other words, if this was minus 2, I would use h equals 2. I would not say h equals minus 2. So take special notes of the difference in sign. In sign for h. All right? So whenever we're pulling our vertex out from vertex form, we need to always be careful that when we pull the h out, it's kind of the opposite sign of what we see in the equation. So if I see a minus 2, that implies negative 2. We're going to take the opposite sign. We're going to take out a 2 instead. That's something to be very careful of. It's a very common mistake, so always try to catch yourselves on that. Now, well, it tells us the vertex, but it also gives us more information. What else does it give us? Well, we get to look at that a. So a is still that leading coefficient, right? And what's going to be so nice is, well, let's think back to it. We had two types of parabolas. We had a parabola that opened up like this. We had a parabola that opened down. So we have a parabola that opens up and it opens down. In the opening up case, our vertex becomes a minimum. In the opening down case, our vertex becomes a maximum, or relative min and relative max. And what the A is going to do for us, why it's so important, is depending on the sign of A, that tells you immediately whether it's opening up or it's opening down. In other words, if A is greater than 0, so if A is positive, then you get a parabola that opens up. And if A is less than 0, then we get a parabola that opens down. All right? So that's very important to know. So not only do we get our vertex, we all automatically understand whether that vertex is a max or a min. That's pretty powerful information. So that's kind of the big reason why this vertex form is so popular and why it's so useful. It just tells you so much about your graph without even having to graph it. So then, go ahead now and pause the video to copy all this down if you haven't done so already. Great. Now, so that's nice and all to understand that we have this useful form we can use, but as we've seen a lot in this class, whenever we're using quadratic equations or functions, a lot of times they're just written in general form, right? They're not written in vertex form. Well, if vertex form is so nice to use, but I'm given an equation in general form, the logical thing to ask is, well, how do I transition from general form into vertex form? How can I rewrite a quadratic function into a vertex form? Let's go ahead and tackle that question now. So, question. How do we write a quadratic formula or quadratic function? How do we write a quadratic function from vertex or from general to vertex form? So how do I transition between my two forms? How do I get from one to the other? And the answer to that question, I've actually already mentioned. So if we go all the way back to when we first introduced the idea of quadratic equations, back then we'd go ahead and list off a bunch of ways we could solve quadratics. We said ways we can solve quadratics are factoring, quadratic formula, the all-time best, the all-time greats, our buddy, quadratic formula, and there was another one in the book called extracting square roots, I believe, and then there was a fourth way, and that was completing the square. And I said we weren't going to talk about it, we were going to save it for later. Well, later has come. So the answer to this question is we complete the square. All right? Now, completing the square is actually a whole process. It's a whole process of taking a general form quadratic function and manipulating it and writing it into the new form. And the new form you write it into is actually vertex form. It's a very interesting process and has a lot of cool math tricks behind it, but I'm going to go ahead and skip through the process. I'm just going to give us the end result. So if you are interested in seeing how the actual process, the steps that go from general form into vertex form, I'd be more than happy to show you through Zoom or anything like that. But for now, I'm just going to go ahead and give us the end results. Start. Okay, sorry for the sudden cut, but in the previous edit of the video, I had a mistake, so thank you very, very much to the student who pointed it out to me. Kudos to you. You are the A+ student for the week. But with that out of the way, let's go ahead and fix my mistakes, which through the magic of editing, no one will ever have to see again. Now then, so just to recap, if I want to take my quadratic function and go from general form to vertex form, the way we do that is through completing the square. I'm going to skip over the actual steps of that process. It is quite interesting, as I already mentioned, so if you do want to see how that goes, just go ahead and ask me. We could talk about it through Zoom or something like that. But, so, the end result. The end result of this whole process of shifting is to get our vertex form, right? Which is f of x equals a times x minus h squared plus k. That's the whole goal of this process right now that I'm skipping over. Is you just want to go from your general form into this vertex form, okay? And what happens in that process as you work through the steps, you discover something. You discover there's actually formulas that make h and k. And so for us, whenever we want to move from general form to vertex form, all we need to make sure we do is understand what the formulas for h and k are and just use those formulas. We don't actually have to go through this process of completing the square. And so regardless of that, what you discover as you complete the square is that the formula that generates h is minus b over 2a. And the formula that generates k is c minus b squared over 4a. So, these are our two new formulas, right? And what it breaks down to is, what this means for us is that if we ever are given a quadratic function in general form and we want to translate into vertex form, all we have to do is apply these functions and then plug whatever values we make into our vertex form. That's all we have to do. It becomes an incredibly straightforward process, not that hard to do. The one thing we have to make sure we understand though is, how do we actually use these formulas? How do I actually find my h and how do I actually find my k, right? To find h, I need these values b and a. To find k, I need these values c, b, and a. So what exactly are these values? What is c, what is b, and what is a? Well, this is where we take a step back and we just remember, how did we begin this process, right? This whole process began with starting with general form and then transitioning into vertex form. And once we remember that we started with general form, right? What is general form of a quadratic equation? ax squared plus bx plus c. So that's exactly what these a, b's, and c's are. These are the values that are from our general form of the quadratic function. So that's a pretty important point or note right there. Is that a, b, and c come from the general form of the quadratic function. So just to recap, what is it? For this class, how do we transition from general into vertex form? All we need to do is use these two formulas, find out what our a, b's, and c's are, plug them in, plug h and k in, and don't forget to plug a in as well. And there you go. Easy as that, you transition straight into vertex form. So on that note, why don't we go ahead and transition into an example now and actually use these formulas. So if you haven't done so already, go ahead and pause the video to get this all copied down, and then we'll go ahead and start our example. Okay, so the example we're going to do is this. This will be our example. A pretty straightforward one. We'll identify the vertex and graph. We'll just do these two things. And the function we'll be concerned about is this. F of x equals x squared plus 3x plus 10. So, right? We want to identify the vertex, but we are given a quadratic function in general form. So in other words, if we're in general form, I want to know my vertex is. Let's go ahead and transition into vertex form. And for us, vertex form is a times x minus h squared plus k. And we now understand that h is found through the formula minus b over 2a, and k is found through the formula c minus b squared over 4a. Great, right? And to actually use these formulas properly, we just need to understand what are a, b's, and c's, which we've had plenty of practice with, so this should not be a difficult step for us at all, right? Hopefully we can all easily see that the a value for us is 1, because 1 is what's being multiplied to x squared. B is 3, because that's what's being multiplied to x. And c is 10, because that is the constant value. And once we have these, it's just a matter of plugging into our formulas. Do some quick plug and chug. So then, plugging into my formula, I get that h equals minus 3 over 2 times 1. So in other words, h is minus 3 over 2. And k is 10 minus 3 squared over 4 times 1. Right, so 10 equals 9. Oh, 10 minus, so this will equal 10 minus 9 over 4, right? And then we can just simplify down from here. So 10 can become 40 over 4 minus 9 over 4. So we get a k value of 31 over 4. And there it is. As easy as that, we can generate the vertex just by using these two formulas and plugging in our values. So I'm going to go ahead and erase the work now to move on to graphing it. So if you haven't done this already, go ahead and pause the video and get all this copied down. Alright, so let's go ahead and make our quick sketch of the graph. So we now understand that when written in vertex form, which let's just copy down one more time. So when written in vertex form, our function will look like this. We need to plug in the value of a, which for us is 1. We need to plug in the value of h, which we found to be minus 3 over 2. And then plug in the value of k, which we got to be 31 over 4. Right? And then cleaning this up a bit, our new f of x, or the same f of x just rewritten, becomes x plus 3 over 2 squared plus 31 over 4. Wonderful, right? And so that means we can identify the vertex as being minus 3 over 2 and 31 over 4. There we go. Now, I do want to make a quick a quick mention, I should say, is that when we're identifying the vertex, right, so for us there's going to be two ways in which we usually identify the vertex. We calculate it using our h and k formulas, or we pull it straight from an equation, like an equation like this. So the note I want to make sure we all understand is that when you're identifying the vertex from the formula, when you're identifying the vertex from the equation, so you already have an equation in standard form. As I already mentioned, you make sure you take the opposite sign for h. So here we have a plus 3 over 2. We take the opposite sign. That is why the h here is minus 3 over 2. Now with the formula, however, when we have h equals minus b over 2a, just use the value the formula creates. So, right, so the formula we saw just created minus 3 over 2a, minus 3 over 2, so that's exactly right. So the point I'm trying to get at is when you're pulling your vertex from the equation, make sure you take the opposite sign for h. When you're identifying your vertex using the h and k formulas, just use the values those formulas create. Alright? Now then, let's go ahead and make a quick sketch of this graph. So, which won't be too hard for us, because we understand our vertex is at that point right there. So minus 3 over 2 is going to be negative 1.5. So we're going to be right there. And then 31 over 4 is close to 8. It's like 7 point something. So 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. So we're probably like right there. 31 over 4. So we get a nice point right there. And then we can understand further, right, our A which equals 1. 1 is greater than 0, so since our a is greater than 0, we must have a parabola that opens up. And so we can create a quick sketch, just like that, and there you go. And yeah, so that's it. There's the whole example. We can identify the vertex quite easily, create our vertex form, and then using the information the vertex form gives us, we can create a quick sketch of the function. Not that horribly complicated. So go ahead and take a moment now to pause the video and get all this work copied down, and then we'll move on to our next example. Alright, wonderful. So, for the next example, we'll go ahead and do the same exact directions, but with a different function. And the function we're going to use this time is minus 3x squared plus 12x plus 1. Minus 3x squared plus 12x plus 1. Okay? And we're going to do this example a bit differently. How we're going to do it differently is that now I want everyone to go ahead and pause the video and try doing this entire problem on their own. Give it your best shot. Okay? And after you unpause, I'm not going to show any of my work. I'm just simply going to give the answer, and we're going to compare our answers. Alright? And since this is already my second edit of the video, please do not feel discouraged if you get a different answer than I do. I could probably have done it wrong a second time. So definitely don't be discouraged if we don't match up. Just go back, check your work, see if you find any mistakes. And if you don't find any mistakes, definitely call me out again. But hopefully I'll be able to get it right on the second go around. Alright, so go ahead and pause the video now. And wonderful. So here's the answer I got on my second go around. I got a vertex of 2, 13. So I got a vertex of 2, 13. And my graph then it looks like this. So 1, 2, 1, 2, 3, 4, 5, 10, 11, 12, 13, x, y. Right, and quickly I can see that my a is less than 0, so my parabola should be opening down. Also, I can quickly identify that my y-intercept is the point 0, 1. If you can't see those things quickly, that's no problem. They're easy to just work out and figure out. But regardless, so with those 3 pieces of information, I can create a quick sketch of my graph that looks something like this. And so there it is. There's the answer, or at least my proposed answer to this example. Hopefully we got the same thing. If not, double check your work and let me know. But with that out of the way, let's go ahead and move on to our next type of example. Okay, so here will be our second type of example. Let's go ahead and find the equation of the parabola, or in other words, let's find the equation of let's find a quadratic equation whose vertex is -2, -2, and that passes through the points 2, 5. All right. So I have to have the vertex be -2, 2, and if I plug in 2 into this equation, it should output 5. That's what we're looking for. Now then, well, we understand something. We're talking about parabolas. So why not let's go ahead and see if we can create a quick sketch of this graph for this parabola just using these 2 points. So I understand that's -2, -2. I understand -2, -2 is going to have to be the vertex, all right? And that's 2, 5 is a point that lies on the parabola. So what does this let us know then? Well, I know that the vertex is the point where the behavior changes. So it's either the minimum or the maximum, right? There will be no points either below this or above this depending on whether it opens up. However, I also have a point up here. So if this is supposed to be the vertex and I have a point up here, that already tells us, that is a guarantee that the parabola has to be opening up. It must look like that in some manner. We already know that it has to open up. So parabola must open up. In other words, what do we know has to be true about the a we're going to make? We know that a must be greater than 1. Oh, actually, my bad, greater than 0. a has to be greater than 0. So we have a nice little check in our head. If we go through all our work and we create some equation, and if for that equation a happens to be less than 0, we know we made a mistake somewhere. Just by having a good solid grasp of the concepts, we can form for ourselves a nice little check like that. So, with that in the back of our heads now, let's go ahead and try constructing what the equation to this parabola is. Well, how should we start it off? Right? They give me points to use. How can I use those points? Well, then it just goes back to the power of that vertex form. Vertex form allows you to directly take away the vertex for your parabola. In other words, if you know what the vertex is, you can plug that into your vertex form. So vertex form is f of x equals a times x minus h squared plus k, right? This is the formula I want to make. I want to make some equation that looks like this. We already know what the h and k are. It's -2 and -2. Wonderful. Well, so in other words, we have that f of x must equal a times x plus 2 squared minus 2. Now here's the problem. The problem is, what's a? That's the last unknown, right? We want the only unknown in our equation to be x. So I need to figure out what a is. Well, how can I do that? And at this point, this is where you just need to take a step back and say, well, what did my problem give me? It gave me the vertex, great, and it gave me another points. Well, I've used the vertex. Have I used the other point yet? Well, no, I haven't. What happens if I plug that point in, right? What happens if I try to plug it in with the equation I currently have? Well, I have 2, 5. All points in the Cartesian plane are x, y. So that means I have an x value of 2 and I have a y value of 5. In other words, f of x, which is the same for y, which is the same thing as y, becomes 5, and I get a times 2 plus 2 squared minus 2. And all of a sudden, I have one equation with one unknown, a. And just like that, it becomes a simple, pretty straightforward manner to solve for a. So why don't we go ahead and do just that? So in order to do that, I'm going to go ahead and erase this little check on the side right here. So you haven't written this down, go ahead and pause the video to do so quickly. Okay. So then, all we have to do from here is solve for a, and we get that 5 equals, a times 4 squared minus 2. So we get 7 equals a times 16. A equals 7 over 16. And there you go. We've solved for that one tricky unknown we didn't know. And now, since we know a, and we know our vertex, I can create a full formula for this quadratic equation. And that formula is this. So I'm going to go ahead and erase this portion right here. So if you haven't done so already, pause the video to copy down. Alright then. So with all the information we have at hand now, we can finally state with much certainty that f of x must be 7 over 16 times x plus 2 squared minus 2. This is the equation of the parabola whose vertex is -2, minus 2 and passes through the point 2, 5. There it is. All right. What's a quick check we can do? Well, a good check is we plug in 2 and we better output 5. There it is. All right. So just to recap, I'm going to go ahead and erase the portion right here. So pause the video if you haven't gotten a chance to copy that down. So just to recap on what we did for this problem, right? Given the vertex and a point on the graph, we can construct, so given vertex and a point, we can construct the equation construct the equation of the parabola by plugging in our vertex and plugging in the point and then solving for a. And we solve for a, right? And as we're solving for a, we have that mental check in the back of our head. We can do a quick sketch of the graph, and we can understand for this example, we were opening up, so we expected a to be greater than 0, which we do have. 7 over 16 is greater than 0, passes that mental check we have. So that's all this problem basically boiled down to, was to understand what your variables meant, to understand what the points mean and how you could use them, and then using that to solve for our one big unknown, which was a, and then constructing our formula. So there it is. So why don't we go ahead and do now another problem very similar to this. So if you haven't gotten a chance, pause the video and copy all this down. Alright, so the next example we'll do will be this. Same format of the question, but this time our vertex will be 2, -1, and our point will be 4, -3. Okay? So this will be our new equation. Again, find the equation of the parabola whose vertex is the point 2, -1, and passes through the points 4, -3. Now, for this example, I want you guys to go ahead and work on your own. So go ahead and pause the video now. Do all the work, see if you can figure out what the answer is, and when you unpause, I'm simply going to write the answer, and we'll see if we match up, alright? So go ahead and pause now. Okay, so what did I get? Well, for this problem, I got the following equation. F of x equals minus x minus 2 squared plus 1. So the function I got was minus x minus 2 squared plus 1. Alright, so go ahead. Hopefully we have the same answer. If not, double check your work. And if you feel confident enough, I could be wrong, so call me out and we'll talk about it more then. Alright, so there is our next example. Let's go ahead and move on. Okay, so for our last example, and to end the video today, I thought we'd go ahead and do a word problem. And the word problem is going to be this. So once during a family picnic, my mom finally got enough. Sick and tired of my antisocial ways. Went over, grabbed my phone, and hurled my phone into the air. Alright? And my phone can be modeled by this equation. So the trajectory of the phone, the trajectory my phone took, or the path it took through the air, can be modeled by this equation. H of x equals minus 2x squared plus 40x minus 183. Alright? So, where x is the horizontal distance, and y is the height my phone reaches. So the question I'm going to ask is, well then, what was the tallest height my phone got, or my phone reached? Right? How high in the air did my phone go? So then, let's go ahead and take some time now to figure that out. So, I'm going to go ahead and, as you can see, I have no board space, so go ahead and pause the video to copy this question down, and then we'll go ahead and tackle it. Great. Now then, let's go and copy the equation down. Beautiful. So, let's go ahead and just understand this. Alright, our goal is to find the tallest height, and we understand that h of x represents height. So in other words, we want to find the max h. We want to find the max h of x. That's what we want to find. Now, we understand something. Our equation is a quadratic. So our graph will have to be a parabola, right? But we can say even more than that. Going back to it, we have two types of parabolas. one that opens up, and one that opens down. Which one do we have here? Go and pause the video, take a couple seconds, see if you can decide. Right? So, which type of parabola do we have here? Well, it goes back to the idea of the leading coefficient determining whether you open up or down. And for us, our leading coefficient is 2 or minus 2. A equals minus 2, which is less than 0. So that means we have a parabola that opens down. Well, why is that important? Why is it so important to understand that my parabola opens down? Well, if I'm trying to find the max, I know clearly then where the max happens, right? The max, if I have a parabola that opens down, must be at my vertex. Because for vertices of a parabola are always the relative max or the relative minimum, depending on whether your parabola opens down or it opens up. So since I have a parabola that opens down, the vertex of that parabola must be my relative minimum, or my relative maximum. Max, right? And the vertex is going to make up of an x and an h comma x. It's going to have my vertical distance and my height. So my tallest height, my max height, is simply the y value of the vertex. And there you go. That's what this problem becomes. It simply becomes, what is my y value of my vertex? Right? So before we get into finding what that value is, I just want to take a moment to talk about this again. To walk through this whole mental exercise we just went through. We were presented with this word problem. The word problem just said, find the tallest height, given this equation. Nowhere did it mention the word vertex. Nowhere did it mention the word parabola. Nowhere did it mention the word quadratic. It was on our own. We had to read this problem and understand, what is the equation I'm looking at? That is a quadratic equation. What do I know about quadratic equations? I understand their graphs are parabolas. What do I understand about parabolas? I understand they have a special point. That point is known as the vertex. What's so significant about the vertex? Well, depending on whether my parabola opens up or down, that vertex must be the relative minimum or the relative maximum. So if I'm looking for a tallest height, if I'm looking for a maximum value, ideally I want a parabola that opens down. Because if I have a parabola that opens down, then the vertex of that parabola is exactly the answer I'm looking for. Well then, the question stands, do I have that? Do I have a parabola that opens down? And quite quickly we can say yes, yes I do, because we understand that our leading coefficient is less than 0. So that's how we bring all this information together. Nowhere did the problem push us or indicate to us we want to think about vertices and parabolas and stuff like that. This is where we had to sit down on our own and just understand. Use the knowledge we now have to piece together the hints and lead us towards this now clear objective for the problem. Alright? So let's go ahead and actually find out what that number is. And luckily for us, we remember that the vertex is h comma k. And we have a clear formula for k. K is the value c minus b squared over 4a. C in this problem is minus 183. B in this problem is 40. So we have 40 squared over 4 times a, which is minus 2. So all we need to do now is plug and show. So I'm going to go ahead and erase this kind of thought process I had. So go ahead and pause the video now if you didn't get a chance to write that down so we can actually calculate this number. Alright. So, calculating that number, because I'm not going to do that in my head, 40 squared divided by 8. So we're going to end up with k equals minus 183 plus 200. So we get that k equals 17. And I don't know if I mentioned in the problem, but we'll go ahead and assume that our units of measurement are feet. So 17 feet. So there it is. There's the conclusion to our story. On that fateful day when I finally pushed my mother too far, she grabbed my phone and she hurled that sucker 17 feet into the air. I can only leave you to guess the fate of my phone after such a fall. But that's it. Yet again, I do want to emphasize this word problem. I like it a lot because it just, nowhere in the problem does it tell you what to do, but by understanding, have a strong grasp of the concepts we talked about today, the path to the answer becomes quite clear. But besides that, I hope everyone has a nice rest of their day, depending on when you watch this. Continue to stay safe, continue to stay clean, and I'll catch you guys in the next video.